Okay, 13.2. Here we go. It's on the derivatives and integrals of vector functions. Good news, you know how to take a derivative, you know how to do an integral, so it's going to be a lot of practicing of that because we're going to find that, hey, it's component by component. And so just like limits was. And so I'm not going to say hot diggity dog, I'm going to keep from saying that today. So here's my paper, um, am I on Zoom? What do I got going? A little bit of Zoom going on here. So this is 13.2, page 6 in your note packet. Of course, I say the page number, and I'll be unhappy about that if I ever try to use this video again and correct something on there. So I'm going to try not to say the page number. Anyway, the derivative. Um, this is the definition of the derivative. The derivative is the tangent vector to a space curve given the direction, gives direction, not slope. I need to slow down. And and so I wanted to show you a little graphic on the animation, and you can look at it here. It's the graphic of this, and it's kind of the idea that it's showing is as the 2 points P and Q get closer and closer together, the distance between the points is getting close to zero. H is the distance between those as those two vectors, the p vector and the cube vector, become one vector, then that's going to find the slope at that particular point. And so that's what we're looking at, the slope for right there at p. So they've done a really nice job in your book, and you can turn all kinds of things on. And when you use I wish I could make it bigger. I did learn that I could zoom in on it yesterday. Yeah, I know I'm not tech savvy, and uh, you can become my tech editor if you like, and help me make it a little bit better. But and did I decide that it was a little better without the light on for this? Okay, so you can just kind of go on here and you can just kind of explore. The vector R is in black, and it's going to be outlining the curve. So if I move it around for different values of t, you can see that the vector R is pointing to the curve at a certain point. If I turn on the R prime, that's the derivative, that's the slope at that point of the curve. And you can kind of, well, yeah, that's what I would thought it would be. It's coming on there in red. And if you want to, you can look at different things if you want. So if you're just kind of interested in what about when these vectors get closer together. Right now I have h being 0, so they should be, my h is being 0.05, so almost 0. So if I make the h a lot bigger, man, it's kind of sticky. It doesn't want to move. There it goes. If I make the H be a lot bigger, you can make this bigger on your screen if you decide to do it. Go on there, but I can't do it on my iPad. I'm sorry, I'm technology challenged. And but you can kind of see that that vector now is in it's in green, and you can see that they're kind of far apart because they're 1.5. And as I move this closer, although it's kind of sticky because I already told you that I had to pull off some stuff, you can see that vector there in green, and you can see that as I get this closer and closer to 0, that h being closer to 0, that it's getting really, really close to being, as I'm at 0.3, and so it's getting really close to being right there, the two vectors together. Anyway, you can explore on it. It's kind of fun. I think it's kind of fun just to make the derivative and r go so that when you move it around for different t's, that you can see the vector and you can see the derivative, and you can kind of imagine that it's the slope at the given point, the head of the vector, the terminal point of the vector on the curve, and you can just kind of drag it around and see. Okay, so we're going to do some of these. So that was a lovely job on there. More light. That was that page. And they tell us on this page here that to take the derivative, all you have to do is take the derivative of the components. And that doesn't matter if you have it in vector form or if you have it in ijk form, vector form. Take the derivative of the components, take the derivative of the components with your ijk. Uh, when when t is time, um, r of t can be thought of as, this should have been the derivative, right? Should be thought of as, this should have been, ooh, that's a typo. This should have been r prime at t, can be thought of as the velocity at a certain point on the curve. And if you want proof, hey, the proof is in your textbook. So they do a lovely job of proving that if this is your r at t, your position vector, then this is your this is the derivative, and it's the velocity. So here I'm going to look at an example in 2 dimension because they're easier to draw, and so that you can just kind of see what's happening on here. And so it's asking us first to sketch it. And remember, when we're sketching it, we let x equal the first coordinate, e at t, and y equal the second coordinate, with e at negative 2t. And then you see if you can put these together. And so kind of my thought in putting them together is, I know that this is e at t raised to the negative 2. And then I know that e raised to the t was equal to x. So this is y equals x to the negative 2, which is y equals 1 over x squared. And I know what that looks like to draw it. So I'm going to come over here, and this is just in 2 dimensions. I just have 2 coordinates, so in 2 dimensions. And I remember this is like, the 6 graphs that you need to know from pre-calc 1. I have a bad habit of putting the arrows on the ends, and I'm going to stop that bad habit in here because sometimes they're looking for direction. And when they do direction, they do put it on the curve and not at the ends of the curve. That's what I'm seeing anyway as the notation for that. But yeah, there's a lot of times that there's 2 things mean the same thing. Kevin and I had a huge debate on that just today. And so, not a debate, the discussion of why it's confusing when that happens. Then the next thing I want to do is I want to find the point of tangency. And so we want to find where they're wanting to find the tangent. So all they're asking me to do is put into r, they're asking me to find r at 0. And this is the point where we're going to have, this is the point on the curve where we're going to go and find the tangent. And so that's e at 0, and then e to the negative 2 times 0. And so that's at the vector 1, 1. That's the vector 1, 1, and it's pointing. So the vector 1, 1 is pointing here, and then the point is equal to 1, 1, right? Because it's the terminal point. So I know sometimes we get confused. Is it a vector or is it as a point? So there is a vector here that points at the curve, and the point that it's pointing to on the curve is the point 1, 1. Okay, and it goes from the origin to that curve. And then find the tangent vector at the point of tangency. So how you find the tangent vector is you find the derivative. And so r prime of our vector here. So the derivative of e to the t, it's off my page, but the derivative of e to the t is, good news, e to the t. You guys knew that. And do you guys remember what the derivative of e to the negative 2t is? I hope you're saying chain rule. I hope you're screaming at the screen, chain rule, chain rule. I got to use the chain rule. So it's the same darn thing, e to the negative 2t. And then I have to multiply by the derivative of negative 2t. So I'm kind of thinking, I always thought of as the outside function, and the outside function was e raised to, right? And when I take the derivative of that, I get e raised to is what I get. Then the inside function was negative 2t. And when you take the derivative of that, you get negative 2. And what do? You multiply them together, and you evaluate at the same inside. And so, yeah, so this is going to be negative 2 times negative 2t, right? E raised to the negative 2t times negative 2. That's hard to say, negative 2 here. and that's a vector. And they wanted me to find it at the point of tangency, and they said that t was equal to 0 is what they wanted. And so I'm going to put in here r prime at 0. And so when I do, I'm getting this vector, which is 1. And when I put in here, I get 0. So I'm getting -2 as this vector. And this is our tangent vector. Now, if you were to plot this tangent vector, I'm going to plot it. And so I'm going to come over here, and the terminal point is over 1-ish, down to 1, 2. So somewhere here, and this is my vector. Now remember, and that's my tangent vector. Remember, you can move vectors where you want. And so if I wanted to come and I wanted to move this vector so that it's right here at this point, so take this vector right here, which was over 1 and down 2, so parallel, right here. And so I'm trying to draw this same vector right here, move it right here. And so there, so you can see that, oh yeah, it looks pretty tangent right there. Okay, so we did a lovely job on that. That's all they were hoping for on it. And now we're off to the races. Where did I put that other paper? I don't even know. And so here's a little bit more difficult example. And so it's asking me to find the equation of the tangent line at the point 2, 1/3, 1/4. So the things that I need in order to find the equation of the tangent line is I need a point on the tangent line, and that point should also be on your curve. So they're telling us that this is a point on the curve, and that's where I want to find the tangent, and that's where that's my point on my tangent line and my point on my curve right there. Then you need the tangent vector, they call it, and you can call it the direction vector of the tangent line if you want, because that's what I need. Because what do I need in order to find the equation of a line? I need a direction vector, and this is the direction vector of the tangent line. So so that's what I need. And so number 1 I was given. Number 2, in order to find it, I need to find the derivative is what I need to find. So if I go to find the derivative, you just find the derivative of the pieces. So the derivative of this is pretty nice. And when I use the chain rule, I'll be multiplying by 1 because the derivative of t plus 2 is 1. And so should I put it in vector notation, or should I do ijk like they've done? I don't like ijk as well. Oh, and I forgot to put my signal up that I found the derivative, right? The prime. Okay, so I'm finding the derivative. So this is 1 over the square root of t plus 2 times 1, so I. And then I want to find the derivative here. Your choice. Oh, am I missing a 2? Sorry. 1 over 2 times the square root of t plus 2. Sorry. I'm glad that somebody told me about that. I don't know why I forgot the 2. It can happen. It's probably because I should have written it like this so that I wouldn't forget the 2. And so then, when I take the derivative, I move that down in front and take away 1. So this would be 1/2. And then t plus 2 to the -1/2. And I'm like, oh, I almost forgot that too. That was crazy. Hadn't done that on a really long time. This one I probably would not use the quotient rule on. I probably would think of it as t plus 1 raised to the -1. And again, I'm pretty lucky because the chain rule, I would get away with it if I forgot it, because I don't often get away with things when I forget it. But the derivative of t plus 1 is 1. And so I get pretty lucky there. So this is raised to the -2, and this is j. And then 2 divided by t squared plus 4. You could move the t squared plus 4 upstairs, or you can use uh, the quotient rule, whichever one floats your boat. It doesn't really matter to me which one you use. I'm looking at how much room I have over here, and I'm a person that likes to use the quotient rule unless I have one, but you don't have to be. And so if you don't want to, so I'm here using the quotient rule, so I'm telling myself I'm going to use the quotient rule, and I'm kind of having this as my side piece of paper. I like to write out my stuff because that's the baby way of doing it. And I like to teach people who are babies how to do things. I'm just kidding. It's the baby way of doing things. And so I've written out the pieces that I need for my quotient rule. And then to even make it more babyish, I say crisscross applesauce. Because it's the quotient rule, I start in the denominator and I multiply those together, which gives 0. And then I minus these together, which gives minus 4t. 2 times 2t, and you subtract them, and then you square this bottom, so you square it, so t squared plus 4 quantity squared, and that's the quotient rule, and that's my derivative for k. And so I'm going to put it right here, so minus 4t over t squared plus 4k. And I want to evaluate this at this point right here. But that value right there, that 2, is not t. That value right there is x. That's what that value is. And this value right here is x. And do you agree with me that if my value for x is 2, then, well, is it a coincidence that t is 2 right there? It definitely is a coincidence. It's not 2 because this is 2. It's 2 because what would make the square root of t plus 2, what value would make that equal to 2? And it's just coincidence. Whoops. It's just a coincidence that it's 2. We got 2's running everywhere, and it is totally a coincidence. When I square both sides here, I get t plus 2 equals 4. Of course, you can see the answer and you take away 2. So t is 2, but that is a coincidence that t is 2. If you would have tacked here, then you need the value when y is equal to 1/3. And you notice that if you want 1/3, then t has to be 2. It should work here as well. And so because this point that we're looking at should all be the same value of t. And for this point, t happens to be 2. Coincidence that it's the same as the x coordinate, but that's a coincidence. You notice it's not the same as the y coordinate and not the same as the z coordinate. And so we did a nice job finding t is 2, because what we want to do is we want to find the tangent vector. And so we're about to find the tangent vector by plugging in. And so we're going to come right here and we're going to plug in t is 2. So we're going to be finding r prime at 2. So when I put in 2 here, I get the square root of 4, which is 2, and 2 times 2 is, so I think 1/4. Do you guys agree with me? And so I'm showing my work along. I'm plugging in 2 into here. It might be better for me if I thought of that instead of the way it's written, if I thought it as minus 1 over, right? And then when I put in 2 plus 1 raised to the, do you guys agree with me? That's looking 1/9-ish, isn't it, Jay? And I think I'll just come back on it. And then minus, and then 4 times 2. I put that one in my head, but then I realized, I'm going to mess this up. And so if I don't write it out, you do things in your head and you mess it up, and then people don't even know what you did. And so I probably should have I should have showed my work there. And so I'm going to humbly repent, and I'm going to put in my work right here. 2 plus 2. I'm plugging in 2. And so here, and in fact, I'm going to be honest with you guys. I did this example earlier, and I did all of this math in my head, and I made a mistake on my arithmetic right here because I looked over and I peeked over and I was getting a different value than what I'm getting right now. And I'm like, did I do it wrong earlier? Yeah, well, when I did it earlier, I was doing multiple things. I was trying to eat my lunch, and so am I getting here 8 over 2 squared is 4, and 4, did I lose? This is a square here, right? I miscopied that down here. That's a square there. So this should be a square there. So I just miscopied my derivative down, and I'm doing too many things, and so I'm getting so tired. And so this is 8. This is 4 plus 4 is 8. 8 squared is 64. And 8 divided by 64 is 1/8. And so, and you can put it in your calculator, and I hope you do. And I hope you get the same. But I made an arithmetic mistake on that one right there, and it can happen. And so definitely it can happen. I have a calculator here. And now I know my vector, right? I'm going to write this vector. This was at 2, not at t. So I'm going to put my 2 here, and I'm going to write this vector 1/4, negative 1/9, and negative 1/8. And then I needed the direction vector. So here it is, right there. There's my my vector at my tangent, and I need at the point of tangency, I needed a point. I was given the point. It's 2, 1/3, 1/4. And now I'm ready to slip it into the equation builder. And for it says up here, oh, it didn't say. It said down here, parametric equation, and then it didn't give a very long line. And so, sorry. And so here's the parametric equation builder. X equals x naught plus AT. Y equals y naught plus BT. Z equals z naught plus CT. And we found the direction vector, the tangent vector is A here, B here, C here. So we're looking at our direction vector for our tangent, and our point, of course, we have right here. So I'm going to call this point x naught, y naught, z naught when I plug that in. So I get x equals x naught is 2, and then the vector is 1/4 t. And then y equals, and then y naught is 1/3 plus, I guess it's minus 1/9 t. And then z equals 1/4 and minus 1/8 t. And that's my parametric equations for this. And I apologize, the line's not long enough. Now the vector equation, I can write that right here. And the formula for the vector is that you take each one of these, right, for the vector equation of the tangent line, and they just use r at t. So just like when you find the equation of the tangent line in 2D, and then you call it y. You know what I mean? And so it's the same kind of deal. And so this is going to be 2 plus 1/4 t. So you put the same thing right here in for the x component. 1/3 minus 1/9 t. And then 1/4 minus 1/8 t for the k. And then boom, we're done. And then the unit tangent vector, well, we just found a tangent vector. So that's what this is at a particular point. And this one is at a specific point. And if we wanted to make it into a unit vector, do you guys agree that all you would have to do is divide by the magnitude? And so that's all this says, that if you want to find the unit tangent vector, so they use a big capital T to mean the unit tangent vector. That's the variable that they use for it. T for tangent vector, I don't know what makes it unit with the, but capital T is what they use for the tangent vector. And what you do is you find r prime at t and divide it by the magnitude. And this will give it to you in general. This was at a specific point, so I plugged in a value for t. but this is going to be at, in general. So we're going to give a little try to that in the next example. So they're asking us here, they're asking us to find the unit tangent vector. So the things that we need to find in order to find the unit tangent vector is that we need to find the derivative of the pieces here. So, and I can use IJK notation, or I can use vector notation with the brackets. Don't mix them together. That doesn't make sense. And so I'm going to use the ones with the brackets. I prefer that. So I'm telling people that I'm finding the derivative, and then I'm just going to find the derivative of the components. So this is the derivative of 2 sine of 2t. So I don't need to use the product rule because it's not 2t. I can just use the 2 hold still, right? And so when I multiply there 2 times the derivative of sine of 2t, the derivative sine of 2t is cosine of 2t, chain rule, right, times 2t. So I would be thinking of the outside function. So if you're just having problems a little bit with your derivatives, you guys are not having problems with your derivatives, and the inside function is 2t. And then I would be saying I'll take the derivative of the outside, which is 2 times the cosine of the same inside, 2t, and then the derivative of the inside, which is 2, comma, and then I'll go find the next one. And when you put these together, 2 times 2 is 4. And so, yeah, I know it's the baby way of doing it. I remember the last time I taught Calc 3, my students said that I was teaching them baby ways. And so, and I was like, oh yeah, I'm sorry. Because I don't often teach them all in a row. And so I get teaching Calc 1 a lot, and I get teaching Calc 2 out of order, and then Calc 3 out of order, and then I'm like, I'm on where are you at on finding your derivatives? So the derivative of cosine is equal to negative sine. So this is going to be negative 3 sine of 2t times 2, right, for chain rule. And so when I fix that up is negative sine of 2t. And then the derivative of 3 is 0. I can't make it any more difficult than that. I can't make it tricky. And then the other thing that I wanted to find the unit tangent vector is that I wanted the magnitude. And so I do like to find the pieces here and then put them together. But you do you. But if you do you and I can't follow what you've got, then and you have it wrong, you have to make it where a person can follow. You need to, examine the work you show versus the work that I show, because that's all I can look at when I'm looking at your lab, or I'm looking at your quiz, or I'm looking at your test. That's all I can look at is what the work you have. So you're going to square the pieces. So this is 16 cosine squared of 2t, right, when you find the magnitude, plus square the pieces, so that's 36. Negative 6 squared is 36. And then when I square this, sine squared of 2t. And then 0 squared. And then all you have to do to find the unit tangent vector, I've written bigger than I did on the first time I did it. So it fit really nice, but I've written huge here. This t, the unit tangent vector at t, the formula is this divided by this. So it's this, r prime at t, divided by the magnitude of r prime at t. And so it's equal to 4 cosine of 2t minus 6 sine of 2t, comma, 0. So there's that vector divided by this. Now, I could have done something had these had the same coefficient. They're not both 16. They're not both 36. So I'm like, oh, I can't really do anything. And so I'm kind of done. Now, they're asking me to find the unit tangent vector at a point, pi over 6. And so we can definitely do that. I wouldn't be tempted to put it back in here. All the pi, t is pi over 6, although that would give you the right answer. I would be tempted to put it in here, but you do you. And so because just because this is going to make such a mess, I'm going to have my 2 times my pi over 6, and then I'm going to have the cosine of that, and then I'm going to have to square that. Then I'm going to have to multiply that by 16. I'm going to have to add it with a 36 and all of that. It's going to be a nightmare, I think. And so what I would rather do, but you do you. So they asked me for this. This is with t. Now they're asking me for this, t prime, so that vector, at pi over 6. So you can just go plug in pi over 6. But that's going to be harder on your algebra. And hey, that, if we can make our algebra nicer, that's what we need to do. So I'm going to find, I'm going to go back here to R, and I'm going to evaluate it at pi over 6. So right here, so this is the cosine of 2 times the pi over 6 times 4. And I'm going to get my calculator in radians. So calculator is in, of course, degrees, because I've been doing other things, and it's in complex mode because I've been using it in my college algebra class. And I think that I need to put it back in regular mode, and I want to get it in degrees. Whoops, setup, I think is, oh no, setup to get degrees. So no, I wanted it in radians. Sorry, I already had it in degrees. And so what I wanted was 4 times the cosine, 2 times pi over 6. And I know what you're saying is that, hey, you did it the baby way again. And yeah, I did. I put it in because I didn't want to make a mistake. So I put it in there all the way. Now I want this to change, but that angle stays the same. So I think I can come in here and let's see if it'll work. And I can get sine. I pushed S to D, sorry. And so I have that angle working, and I want it to be -6. So I didn't really have to type that negative, that angle in twice, but it would have been okay. I could have done it. And I'm right here, -6 sine of 2 times pi over 6, because that's what t is. And I get -3. And oh, I put in cosine. I said I was going to put in sine, and then I put in cosine. Why did I do that? Was anyone paying attention to me? Okay, so now really make sure I got it so you can see what I'm putting in. I'm doing this one right here. So -6 sine, and then I just noticed I had cosine in there. I'm like, what am I doing? And so it's -3 square roots of 3. So I'm going to put that right here. And then when I put in t is pi over 6, I get 0 for the z component. And then now I'm gonna find it right here, just because of room a little bit. No, I'm gonna find it right out underneath it. Room be darned. So I'm gonna find the magnitude. And so instead of putting it in that formula right there, I'm gonna square the pieces, and I'm going to add them. So this is squaring the pieces, square the pieces, and add them. And so you can kind of see that hey, that's a good way of going. It was a lot easier than putting it in there, right? And so 27, I hope I don't mess it up, because that would be embarrassing as I'm saying that it's a lot easier. But if I was to mess this up, which is squaring these pieces and then adding them and then taking the square root of them, what chance do I have there? None. And so this is going to be t prime, our vector, at pi over 6. It's going to be this divided by that. That's why I like to write that out. And that way it's kind of clear what I'm finding, and so that other people can follow me. It's not just important that I can follow myself. And so, but it's also nice that I can follow myself. And it's nice if I can go back and look at what I did 3 days from now and still say, that was my vector, and I'm going to make it look really vector-ish, and still say to myself, oh yeah, I see what I got there. I see what I did. I'm doing okay. And so we did a lovely job on there. If there's a bunch of theorems here, The proofs are in the textbook. And in fact, they ask you to do some of these proofs. And they're the derivatives of vectors. So like if you were crossing two vectors together and you wanted to take the derivative, and so all of these, and I think some of the exercises ask you to use some of these proofs, and this is chain rule for vectors. They've letting you be a vector, just take the derivative of each vector, and then you can add them together. And if you have a constant multiple, and it's just a constant, then you just take the derivative of the vector. And so they're actually what you think they would be, which is kind of amazing. Anyway, so give a look at some of those, and so we're gonna do here. This is a little one thing to prove. Ooh, come down here. One thing to prove, and we're going to see this in the next section, and so anyway, so we're going to give a try to proof of it. They're saying that if the magnitude of r at t is equal to 0, if the magnitude of r of t is equal to a constant, then r at t and r prime at t are orthogonal with one another. Now, if I want to show that these two things are orthogonal with one another, then what would I have to show that they were orthogonal with one another? So I hope that you're remembering back to your dot product, and I would have to show that the vector r at t dotted with the vector r prime at t equals, what would I have to show that it equals if I dot them together and they're orthogonal? Yeah, equals 0. And so that's what I'm gonna kind of try to build on. And all of these kind of proofs have some trick that once you start with, then you can just go with. And so that's kind of the story on them. I'm looking for my phone so I can find what time it is, because I have a dinner date. Maybe my iPad says what time it is. And I have to stop my video for my dinner date in a little tiny bit. And so, okay, so here's the trick, is that you start off with r dot r at t, if you like, r at t dot r at t. And you'll recall from when we dotted two vectors that were the same together, we did this in chapter 12, that was equal to the magnitude at r at t squared. And you can think about it and reason it out again, right? When you multiply the components for x together, for y together, and for z together, right? And then you take the square root. That's what this is, right? When you do the magnitude, you take the square root. So if you square the square root, then you just get the components multiplied together. I said that wrong, but this is, you multiply them together, right? The x's, the first coordinates together, and add up with the second coordinates together and the third coordinates together, but they're equal to one another. And so it's the first coordinate squared plus the second coordinate squared and the third coordinate squared, right? And then that's what the magnitude is square all the coordinates, and then take the square root, right? And then square it. So yes, so those are the equal to one another. And then if I do the derivative with respect to t of this r at t dot r at t, and I do the derivative over here, I think there was a theorem in Calc 1 that said that if you do the derivative of two functions that are equal to one another, that their derivatives would be equal to one another. I think it was in chapter 3, and I think it was something we said, oh, that's, hand waved it. It's obvious. And you can prove it if you like. Now, what those properties that we just looked at said, that if you take the derivative of a dot product, that you kind of use like a product rule. And so, and I don't care how you write that. that you take the derivative, you leave the first one the same, it doesn't matter, and then take the derivative of the second one, and then you add that with, then you take the derivative of the second one and multiply it by the first one. And you're going to notice that what happens when you do that here is that you get two things that are exactly the same, because remember the order of dot product is commutative, and so there's two of these, right? All right, so I got some of them with T's and that one without a T, but I'm going to sneak a T in there. So, I have this one and I have that one, and they're equivalent to one another. And then on this side over here, we were told that R at T was a constant, right? Remember that was given? And so if you square a constant, then you have a constant squared. And so what is the derivative of a constant squared? Well, it's equal to 0. What's the derivative of a constant? 0. What's the derivative of a constant squared? 0. So like if you're taking the derivative of 2, you get 0. If you take the derivative of 2 squared, you get 4, and the derivative of 4 is also 0. So this is 0. So this equals 0. And then all of a sudden you're seeing what I have. If I divide by 2, I have r prime at t dotted with r prime at t, and I have all of a sudden, right, I divided both by 2, I got 0, and all I needed to show that they were orthogonal is that if I dotted them together and their dot product was 0, so thus they're orthogonal. Then the integral, good news. The integral, all you have to do is take the integral of each piece. And so if you have your standard vector where you have a function of f in the x component, a function of g in the y component, and a function of h in the z component, then you just take the derivative of the integral of each of the pieces, and also the derivative of each of the pieces. And also the fundamental theorem of calculus part 2 applies, where if you have bounds, you put in, you evaluate your antiderivative at the upper bound minus the lower bound. So you, the integrand, if you want to call it, or your antiderivative. So we're going to try one right here and see how we do. And so here they're asking me, and this is one that I probably can do in my head, those three pieces of the antiderivative. So I'm going to take the antiderivative of t, and that's going to be t squared over 2, and then that's the I component. And then I'm going to take the antiderivative of e to the 2t, and I don't know if how you guys have it memorized, but I have it memorized where you divide by the same darn coefficient of t, and I don't know if that's how you have it memorized, but that's how I have it memorized. And so, and then plus 3t, and that's my k component, and I want to evaluate that from 1 to 2. And I was taught to draw a straight up and down line to evaluate that, so that's what I do. And so when I plug this in, you do the upper bound minus the lower bound, and I'm going to be putting in 2. So when I put in 2 and I square it, I get 4. Divided by 2 is 2i. And then when I put in 2 here, I get e to the 4 over 2j. Plus, and then when I put in here, I get 6k, and I'm going to use parentheses. I didn't write it in vector notation with the brackets. I used ij and k just because the problem had ij and k in it. And now I'm going to subtract, and then I'm going to plug in 1 for t, and so this is going to be 1 over 2i plus, when you put in 1, you get e to the second over 2j. And then when you plug in 1, you get plus 3k. And then when you do the subtraction, you're going to get 2 take away half is 3/2 I. And then we're going to get e to the 4 over 2 plus e to the second. I can't really add those together. E to the 4 plus e to the second over 2. And that's my j. And then I'm going to get, oh, did I mess up my sign right here? I should have had minus right here. Sorry, just checking you. I'm checking myself too, making sure that I haven't had much sleep. I did find my keys though. 6 minus 3 is 3. Okay. And then I did a lovely job on that. And I think I'm going to have to get Kevin to stitch this video together because I'm going to be late if I don't go. So, oh, how many more do I have examples? Too many to not be late. And, oh, I make myself so unpopular when I'm late, but maybe I can do it. Okay, so here I'm looking at, I have to do the pieces. So I have the integral of t cosine of ti here, right, dt, and then plus, and then the integral of t sine of t squared of dt of j, and then minus, and then the integral of cosine squared t of k. I like to put my dt. Do they put their k on the outside? They do. They put their dt and then their k on the outside of this. And so I kind of have got that going good. So lovely, lovely, lovely. So here you need to use parts in order to take the antiderivative of that. And the way that I was taught parts is by tabular. And so I don't care how you use your parts. I'm not supposed to teach you parts, but I'm going to show you how I do parts. And so I put the part that I can take the derivative. I think that's why it's called parts, because the part of this and the part of that. So the part that I can take the derivative of, I put here first. And you can call it a name if you want, but I don't. And then I repeatedly take the derivative until I get to 0. And then I put the part that I'm going to take the antiderivative of here. This is how I do it. You can do it differently. So I take the antiderivative, and the antiderivative of cosine is sine. And then the antiderivative of sine of t is negative cosine of t. And then I was taught that you do the diagonal and you add them. So the first one is plus. And so this would be, I'm taking the antiderivative of this, would be a positive t sine of t. And then the next one, as you go along here, I'm doing it in purple, but my purple is not much different than my blue, and so it's hard to see that they're different, but that one is minus. And so I get 1 times negative times the negative here, so that's a positive cosine of t. So plus cosine of t. And that is my I component. And then I want to move on and I want to do my j component. Now my j component, I don't have to use parts. I can do a u sub on it. I can let u equal t squared. Then du equals 2t dt. And yeah, I do everything the baby way. And then the integral here will be t sine of u, because I'm replacing u with t squared. And then dt, dt is du over 2t, right? I'm just dividing that in my head. And yeah, the t's cancel out. That was the reason that I did that. And now all I have to be able to do is take the antiderivative of 1/2, because I have the 2 in the denominator, 1/2 u. And so we're going to have the 1/2 out here in the front. And now I've taken I just have to take the antiderivative of sine of u, which is cosine, but it's negative, right? And so I'm going to flip this. I'll just put parentheses around it. Negative cosine of u. And then nobody cares about u, and I know it hurts your feelings, but u was equal to 2t. So instead of leaving this as u, I need to move this into 2t. So I'm going to just rewrite this stuff over here to kind of bring it down a little bit. And then I'll kind of have my answer all cleaned up and not have gotten rid of that work. So this is negative, even though I was trying to jam it in there, cosine of t squared, j. And then the next one over there, I look at it and I'm not, well, I can't use, I can't use parts, like split it apart, cosine times cosine, and then do parts because it's not going to go to 0. And, oh, it might make a wraparound. I don't know. I don't know. I never did it that way. I guess everything's possible. What I do for the cosine squared of t is I know, I have memorized that this is equal to 1/2 1 plus the cosine of 2t. I don't know if you guys have that memorized, but that's the trick to integrating it. I'm probably going to lose that sign. I hope I don't. But if I do, I hope I don't cuss and say something that I would regret, because my mom's probably going to watch this video, and she says not ladylike to talk that way. So anyway, so I'm going to get negative half times, and then the integral of, I'm putting the half in the front, the integral of 1 is t, and the integral of cosine is sine, and it's positive, of 2t, and divide by the same darn thing. And so I'm going to get here half, I can just bring that down, t plus sine of 2t over 2k. And then you remember when you had no bounds? I don't know if you guys remember in your life a time when you were boundless and you had no bounds, and you needed plus c. Well, this is a vector, and so my plus c should also be a vector, and it should have 3 parts. So I'm going to say plus c, and I'm going to put a little vector bar over the top of it to tell everyone that, hey, that's a vector. And so I did a lovely job on that. I'm going to stop right here, even though you don't know that I'm stopping, and so I shouldn't even say that. And I'll come back because I'll have Kevin put these together. Stop. Okay, so let's look at our next example here. So we want to integrate the pieces. So we have the integral of 1 over 1 plus t squared dt. So that's I. And then the next one, the integral of t over 1 plus 2t. I kind of like to, I'm separating them, so that I can just do them individually. And so that helps me to do it that way. Some people say, well, you can leave it together, and you certainly can, but I kind of like to separate it so I can kind of see what I have. dt, and that's k. Okay, so I separated them out, and then I'm thinking about this guy, and I'm thinking, I recognize that. This was dt, and I got di, because when you're writing the same thing over and over again, you lose track of what you're writing. Do you guys recognize what the integral of that is? I hope you do. It's arctangent. And so this is tangent t here. And this is I. And then this one here, I might need to have, I like to kind of be able to, that one's done. But I'm going to have to work here. So a lot of times I'll just bring this down here so that I can feel like, I'm not going to lose that, and plus. And then this, I'm going to have to use a u substitution to do that one, and so if I let u equal 1 plus 2t squared, then du will equal 4t dt. And then this integral, and I know I do it the baby way, but is t over u, and then dt. If you solve this for dt, it's du over 4t, and the t's cancel out on you, so that's wonderful. That's what you were hoping for. And so now it's a matter of taking the integral of 1 over u, the 1/4. You can put the 1/4 in the front if you like. I crossed it out. I don't know why I've gotten so sloppy with my writing, but it might be because I've gotten too tired. Can happen, huh? And so I'm to a point where I'm like, my handwriting is really suffering. So the t's drop out, and I have the integral of 1/4 1 over u. And I don't know if you remember the integral of 1 over u. I hope that you do. And so this is going to be 1/4 the natural log of the absolute value of u. And this is what I mean by, oh, I wish I would have brought this down a little bit further. And maybe I'll just make my arrow a little bit longer, because I like them to kind of line up. It's not so big a deal, but put it all together at the end, I guess, would probably be better. And so I'm bringing that down. But remember that u is equal to 1 plus 2t squared. So that would go in here. Now here's where I don't need the absolute value, because 1 plus 2t squared is always positive. Because if you square a negative for all values of t, this value would be positive. So since this is always positive, and I put it in this absolute value, I don't need the absolute value. And so sometimes students will tell me, but you didn't use the absolute value there. And you're saying I need to use the absolute value here. Well, it depends on whether or not my input there is always positive, or if my input it could be negative. You need the absolute value if it could be negative, because you can't take the natural log of a negative number. And so I feel like I've forgotten something here. I'm looking at it to see, make sure that I haven't made any mistakes. Oh, J, that's what I was thinking. You know, I didn't write something, but I can't remember what. And then now I'm looking at that next one, and do you guys recognize that next one, what this is? And there's two ways that you can do it. It's the arc sign, and so you could, and usually you do it as the arc sign, and so this is minus, because I have the minus there, and then the arc sign of t, k, plus c. If you're saying that you kind of remember the arc cosine, or you're asking what is the arc cosine, so this is my answer here, and I'm all done with this problem here. Typically, we'll use arc sine as opposed to using arc cosine, but the integral, I don't know if you guys remember this, but of -1 over the square root of 1 minus t squared dt. So if I put that negative in there, is equal to the arc cosine of t. And so I think that either one would have been okay, but I think typically they use sine, is what I've noticed. Okay, one more to do in its initial value problem is what it is. And so we're going to try it. And so they're telling us, so that paper's now blowing away. I have the fan on, it's so hot in my house. And and so I have papers blowing away because of the fan. But this is saying the second derivative is equal to this. And then this has given us, it's asking us to find r. And it's giving us, it's giving these initial conditions. It's pretty nice that they've given us to them at 0, but they could have given them at different values. When they give them at 0, I think the math is a little bit easier, so that's kind of nice. So I want to show you kind of how you go on that. Okay, so the first thing I'm going to do is I want to take the the antiderivative of, or the integral, if you want to say, of the second derivative. So if I take, so I literally am taking the antiderivative of this, antiderivative, and I'm taking the antiderivative of this. And so that's what I'm literally doing. And so when I take the antiderivative of this, I get back to the first derivative. And then the antiderivative of this is 1 over 2 square root of t, I. And then the antiderivative of secant squared, I thought I didn't have to break it apart into each individual one there, just because these were so nice that they're all friendly. And so, yeah, if you're thinking tangent, you're right. So this is plus, and then the tangent of t, j. And then the antiderivative of e to the t is e to the t. So minus e to the t, k. And plus c, where c is a vector. It has an I, a j, and a k. And then I'm going to use my initial condition. So it says r prime at 0. I guess I should have my little vector hat on, running around without her hat. And equals, and then I'm going to put in here 0. I took the derivative of that. What the heck am I doing? Did you guys see that? I didn't do that to the rest of them, did I? Well, I might have taken the derivative of this one. I was trying to take the antiderivative, but this is t to the 1/2. I hope you were yelling at your screen. And what you do to take the antiderivative is you add 1. I don't know why I took the derivative. I think it's because I had very little sleep last night. And so I'm going to give myself that that's what the reason is. But remember, you add 1 and divide by the same darn thing. So if I add 1 to the exponent, it's 3/2. And if I divide by the same darn thing, it's 3/2 in the denominator. I never write it like that, though, because I always say to myself, if you're dividing by 3/2, that's the same as multiplying, right, by 2/3. And so this is 2/3 t to the 3/2. And I was like, holy cow, when I put in there 0, this is undefined, and this is going to be a different situation that I remember doing. So when I put in here 0, this part is 0i, which is gone. And then the tangent of 0 isn't the tangent of 0, 0? So 0j, and so that's gone. Now be careful though, because not everything, when you plug in 0, is 0. Like e to the 0, well, that's equal to 1. And so this is minus 1k plus c. And what did they tell us that r prime at 0 was equal to? They said r prime at 0 is equal to I plus k. So this is equal to I plus k. And then the good news is that you can solve this, right? You could add 1k to both sides. And when you do, the dust clears. I get the vector c is equal to I plus 2k. Does that seem okay? And so I love that way of doing it. That wasn't a way that I was ever showed before, and I learned it on a video, and I just love it. You plug in your 0, and then what does that equal? So these two things are equal to one another, and then I can solve this right there, all in one line. How I used to do it is that I plugged in the 0, and then I put that over here, which is basically the same, but I don't know. It's just slick. I think. Anyway, you can think it's slick too if you want. I kind of liked it. I love learning something new. So this means that I'm going to have r prime at t, and it's going to equal 2/3 t to the 3/2 I plus tangent of I, j, tangent t of j, and minus e to the t, k. And then we found c, right, the vector c. the vector c, we just found it. It was I, so plus I, plus 2k. And then I like to regroup these together, all the i's together. So when I do that, this is r prime equals, and then this is 2/3 plus t to the 3/2. Ooh, what am I doing? 2/3 t to the 3/2. This is I, that's I, so this is plus 1, and then I. And then there's none of these for the j's, so just leave the j alone, plus tangent t of the j. And then you have to be careful. You'll make a sign error on the k's. And so if you put minus here, but you need parentheses because these are both going to be k's. So if you put minus there and you have your e to the t, and then you come over here and you put in there plus 2, you'll have a sign error. And so I find that to not make that mistake, the best thing to do is to turn this into a plus right there, so that I can just let everybody have the sign that they have inside the parentheses. So negative e to the t and plus 2 here, and then k. But you do you. But if you have a minus out here in parentheses, it needs to distribute. And so you have to be careful there. Now I'm going to do the antiderivative again. So I'm going to antiderivative again these pieces, and that's going to get me to r, and that's what they were asking me to find. So I'm going to take the antiderivative of this. Remember, you add 1 and divide by the same darn thing. And so I'm going to put that up here. So I have 2/3 t to the 3/2. When I add 1, that's going to be 2/3 t to the 5/2, right? When you add 1, 3/2, I'm off the page, sorry. When you add 1, right, to that, you're going to get 5/2. And then instead of dividing by 5/2, I'm going to times by 2/5. So when the dust clears here, I have 4/15. T to the 5/2. The antiderivative, again, of course, I have it off the screen. The antiderivative of 1 is t, so plus t, I. And then the antiderivative of tangent. I don't know if you guys remember the antiderivative of tangent t. I hope that you do. I hope that it's one of the ones that you have in your on your mind. If you wanted to, you can find it. It's a long process, right? Though, but you could. I mean, you could be down here on your paper, and you could be saying the integral of tangent dt, right? That's the integral of sine of t over cosine of t dt. I'm going to let u equal and cosine of t, so that du equals, I want to take the derivative, so negative sine of t dt. So when I plug this stuff in, u was cosine, so I have my sine, I know it's the baby method, but I have my sine of t in the top, I have my u in the bottom, and then I'm going to times that, replacing dt with du over negative sine of t. The signs cancel out, and I am left with the integral of negative 1 over u du, which is negative of the natural log of the absolute value of u, right? And then remember what u was. U was cosine of t. So this is negative natural log of the absolute value of cosine of t. And so if you remembered that, wonderful. That's one that I just have for some reason in my memory bank. I don't know why. And so this is natural minus, and then the natural log of the absolute value of the cosine of t. And I do need the absolute value because cosine could be a value between 1 and negative 1, and the input into my logarithm needs to be positive. And okay, and then the antiderivative of negative e to the t is negative e to the t plus 2t, and those are my k's, and then plus a constant of integration. I'm going to call it d, and it's a vector. And you don't have to call it d. You could call it c again, or you could call them c1 and c2. It doesn't matter. I was taught to call it d, and so I call it d. And that's just how Mr. Moretti showed us how to do it, and so that's how I do it still. But it's a choice. So when I put in r at 0, r at 0 is quite nice. You have to be careful because it does wipe out some things but doesn't wipe out other things, and so you really do have to make sure. Like, for example, the cosine of 0 is not 0, and e to the 0 is not 0. But these other things, it did wipe out. When I replace this with 0 and that was 0, then I get 0i, and that's gone, right? Done. I don't have to worry about it. But this is the natural log of cosine of 0 is 1, and so this is the minus the natural log of 1. Coincidentally, I'm telling you, hey, that's not 0. Well, it's cosine of 0 is not 0, it's 1. But the natural log of 1, what is the natural log of 1? It is 0. And yeah, I know I forgot my j. I'm going to get it there. There's my j. So this is minus 0j. Then plus, it's the k's again. So when I put in here 0, I get negative 1. Right, negative 1. And when I put in there 0, I get just negative 1k, because that's 0. Plus d equals, well, what did they say it was equal to? Back up here, right? That's a little typo. That little hat is not only on the I, not on the 2, but it grew when I put it in there, when I typed it in there, and I apologize. It'll be something I fix for the real students I have next semester. And so this is 2i plus j minus k. And then I'm going to solve for k. So I'll add, solve for d. So I'll add k to both sides, so plus k, so plus 1k. And when I do that, I get just 2i plus 2j as my answer because the k's go away, right? And so as for my answer for D. So this is what D is. And now I'm just ready to put my answer together, all together. Here we go. Now in the i's is going to be added 2. Is that okay? Because when I add D on here, and I just don't want to write it twice. And so into the i's is going to be added 2. So r at t, our vector, 4/15 t to the 5 halves plus t plus 2. Is that okay? Because that's going to be, that's D, right? That's D. There it is right there. And I'm putting that on there. And so this is i's. Into the j's is going to be 1. So this is going to be, remember how I like to do it plus, and then let them be their own sign. And you can write 1 minus the natural log of the absolute value of cosine of t. That would be good if you wanted. And then those are the j's. And the k's, I'm not getting any for D. I'm not getting any new k's, so k is just the same. So plus, and then negative e to the t plus 2t plus, and then your k. And whew, it was pretty long. Nothing particularly difficult. Just knowing all those different antiderivatives, and I don't know if you remember that big chapter in calculus 2 of all those antiderivatives, and so we gotta get a good time of practicing on them. And of course, what is the one that I mess up? And so right here. And you have to watch yourself. I remember that when I was a student that I would, well, even now, that I have to watch myself. If I'm trying to take the antiderivative, I'll take the derivative, particularly if I get a little bit too tired. And so anyway, that was 13-2. That's the end of this week. Woohoo.